Okay, we have touched on ensembling before a couple of times. Here, there's a little bit more specific focus on why it's needed and some skill improvements that can be shown and various skill measures that are used to do that. So this is about ensemble generation. TIGI here is the Torpex Interactive Grand Global Ensemble. Torpex is the observation system and predictability research experiment. Okay, so these are international projects. TIGI collects hundreds of ensembles from different prediction centers, which gives you a way to compare, contrast, and maybe develop multi-model ensembling to improve predictions and accomplish higher skills overall, and we'll see how that happens. So this is a section title, but more as a statement, so I just left it as a separate slide. Ensembles provide more complete and valuable information than single states. So when we say deterministic forecast, we mean only one integration which used to happen when the weather prediction business started, for example. And probabilistic forecasts evolved out of this ensembling approach, where I said before that ensembles give us a sense of various states that Mother Nature could have taken with different, slight differences in initial conditions. Another way to look at it, maybe a more accurate way, is to say this also represents model uncertainties. So you have errors in initializing the model, and then the model deviates from reality as you integrate forward when you validate against background after the forecast period has passed, for example. But even if you had perfect initial conditions and the observed state was completely known, the growth rates of various events, processes, feedbacks, and so on in the model are different from observations. They are place dependent, season dependent, process dependent, and so on. So model will still deviate from observations. So you can think of the ensemble as model spread or model uncertainty. So we will see a little bit about how to quantify model uncertainties. We saw this way back in chapter 2 when we first mentioned ensembles. So we are looking at 3, 5, and 7-day forecasts here, and the time evolution of monthly average skill using continuous rank probability skill score, what is called CRPSS in short, for 3, 5, and 7-day ECMWF probabilistic predictions of the 500 hectopascal geopotential height, which is a good indicator for mid-latitude circulation anomalies in the lower atmosphere weather. So this is for the northern hemisphere, and this is measured in comparison with climatologically based probabilistic information. So you can see here this seasonality of the dependence, but you can also see that 3-day skill is higher consistently than the 5-day and 7-day skills. But if you compare in time, for example, now the 5-day skill is as good as the 3-day skill back in 97, 7-day skill is as good as 5-day skills, and so on and so forth. So this is the evidence of ensembling, that the ensembles here allowed us to accomplish higher CRPSS, continuous rank probability skill scores, and that's one of the measures. We will look at other measures which are used in the business. Okay, so to think about it, a probabilistic forecast P, that is a certain event will occur. For example, the 2-meter temperature anomaly at a specific point, could be a heat wave, for example, is reliable. So the probability forecast P is reliable if, on average, the predicted event will occur with an O frequency. A way to measure the reliability of an ensemble is to construct the so-called reliability diagrams, which contrast the average forecast probability P against the average observed frequency, i.e., it shows the position of the points P given O. Okay, for many cases, taking into account all grid points within an area. So model has a grid size in which it is computing everything, and the meteorological feature like the 2-meter temperature anomalies over a region, so you average over the whole region. If an ensemble is reliable, the points P semicolon O, P given O, lie on the diagonal, which we will see the figure, so they will be a 1-to-1 match if the model is perfect. The Breyer skill score, which measures the distance of these points from the diagonal, is 0. Okay, so there is a Breyer score, and then there is a Breyer skill score. The corresponding skill score, BSS, Breyer skill score, which is defined as the relative difference between the Breyer score of the forecast compared with a reference, for example, a statistical forecast based on climatology, would be 1 for a perfect forecast and 0 for a forecast that does not provide any more valuable information than reference. So for example, if you're going to just use climatology and say 3 days later the weather is going to look just like today, then the Breyer score is how close you are to the observed weather, let's say 2-meter temperature on day 3. And if Breyer skill score has 0 value, then it will be as good as climatology, as an example, a reference prediction. And if it is skillful, then it will be close to what will be observed on day 3. So here it is, reliability diagram for the ECMWF seasonal S4 prediction of 2-meter temperature anomalies in the lower tercile, so A and C, and in the upper tercile, C and D. And here this is done for Europe. This is done for these are for 2 to 4 month forecasts started on November 1, valid for December, January, February, and have been computed considering the 30-year S4 forecast. S4 is their forecast system. Reforecast, that's the reference, i.e. the forecasts started from November 1, 1981 to November 1, 2010, both included. Remember the reforecasts, it's either a fixed system or a on-the-fly system which does hindcasts to identify model biases and validate, calibrate the model during the forecast mode. Okay. The size of each circle here depends on the number of events in that specific category. The largest, the highest number. So the Breyer skill scores are, so let's make sure here. So the A and B are for the tropics, and C and D are for the European region. So clearly you can see that tropics have a higher skill for 2-meter temperature prediction here. So forecast probability versus observed frequency. So P given O. If the model ensemble is perfect, then you should be on this diagonal line. And when you deviate, your Breyer score is changing, and your Breyer skill score reduces as you get away from the diagonal line. So for A and B, the Breyer skill scores are 0.248 and 0.279. Just compare that to C and D, where it's actually minus 0.053 and minus 0.081. So essentially there is not much usable information for 2-meter temperature forecast, anomaly forecasts for DJF over Europe. Okay, that's for this system. We will come back to this later on. Okay, so the model is reliable. It's the same model, so the processes, the regions, the seasons, everything matters. So tropical skills here are higher. The model is more reliable for the tropics than for the European region. And the other way to think of it is that the schematic of the relationship between the ensemble spread measured by the ensemble standard deviation here, sigma, and the error of the ensemble mean forecast. The blue circles identify ensemble members, so we have initial conditions and final forecasts. So that's the way to represent model error or initialization error, and then the forecast error, right? So the green circles identify the ensemble mean forecast. That's this one here. And two examples. This is the observed state, red circles, the true state of the system. It's many times done as a observation system simulation or system simulation experiment, where you take one of the model realization as reality and measure other ensembles against it to look for intrinsic model skill. Okay, it's just a way of developing statistical properties. A shows that when the ensemble spread is smaller than average, one should expect that the ensemble mean error is smaller than average, and B shows the opposite situation. So here the ensemble spread as a standard deviation and the ensemble mean error. So you can see the error is larger and the standard deviation of the ensemble members is larger. So this itself depends on model configuration, the process that's being modeled. 2-meter temperature may have more skill than precipitation, for example, or a snowstorm in DJF in the mid-latitudes, and so on and so forth. Okay, many details are there in what the actual overall skill of the model ensemble forecast is. Okay, we'll see some details as we go forward.